Recently we've been talking about LTI circuits in sinusoidal steady state, where all the signals, namely all the currents and voltages, are of sinusoidal nature, oscillating at the same frequency, omega. And that frequency is the frequency of the input or inputs that are driving the circuit. For such a circuit, we realize that each signal can be represented by a complex number, where the magnitude of that complex number would be the amplitude of the sinusoidal signal, and the phase of that complex number would be the phase of that sinusoidal signal. Okay, so a time domain signal, a sinusoidal signal, therefore can be represented, which was a very simple observation, by a complex number, okay, or a vector on complex plane, if you will. This at first seemed like just a mathematical trick, okay, but soon we discovered that it has some, it's more than a mathematical trick, it has some physical flavor into it, in the sense that the phasors satisfy KCL and KVL. Or to be more precise, the phasors, or the phasors of voltages satisfy KVL, we showed that, and also phasors of currents, they satisfy KCL. Now this motivated us to look at the terminal equations, also from the phasor point of view, and there we made another remarkable discovery, which was that the inductors and capacitors are dynamical components, behave like just simple resistors, okay, when looked from the phasor point of view. Namely, for a capacitor or for an inductor, the ratio of voltage to current, I'm talking about the phasors, is constant. And that constant we called the impedance, the generalized resistance for those components. Now, since phasors satisfy KCL and KVL, plus the terminal equations, they all boil down to a sort of Ohm's law, okay? Combining those two facts now motivates us to look at the circuits in sinusoidal steady state from the phasor point of view, okay? And that's the motivation for our phasor domain analysis, which we start developing starting from this lecture. Okay, first of all, the goal here is solve the circuit, an LTI circuit, in sinusoidal steady state. Okay, and the procedure is as follows. Step 1. Okay. Transform the circuit into phasor domain by representing the input and circuit variables. We mean currents and voltages throughout the circuit, circuit variables. As, or in terms of their phasors, okay, and passive circuit elements by their impedances. Their impedances. Okay. Now, since impedance means just generalized resistance, okay, after this step, the circuit from the time from the original circuit that we're given, you obtain a sort of LTI resistive circuit. The only difference from the classical LTI resistive circuit is that currents and voltages and also the resistances, which we're now calling impedances, are allowed to be complex. Other than that, there's no difference whatsoever. Okay. Impedances. And then step 2. Now, since in this step we obtain an LTI resistive circuit, we can apply our LTI resistive circuit analysis methods, anything we want, and solve for the asked variables, okay, or for their phasors. Solve the phasor domain circuit using the standard techniques for LTI resistive circuits, treating it like an LTI resistive circuit. Okay. In other words, obtain the phasors of the asked variables, namely, if you're asked for some inductor current or a resistor voltage, what we do is we obtain for the phasor of that current or the phasor of that voltage. Obtain the phasors of the asked variable. Okay. And step 3, the last step, is the easiest of all. Once we have the phasor of the asked variable, let's say of the capacitor voltage, what we do is we transform that complex number into the time domain representation of that signal, since we know the frequency of the oscillations, omega. Step 3, transform the phasors obtained in the previous step into their time domain representations. Okay. And since we're dealing with a circuit in steady state, in other words, we're dealing with the particular solutions, we don't have to worry about the initial conditions of our dynamic components. Okay. Now, the procedure is quite straightforward, okay? But when put in words, it may seem a little bit complicated, but hopefully that complication will disappear when we apply this procedure to a few simple examples, okay? So let's begin by our first example. A very simple topology. We have a sinusoidal source driving following RC connection. Okay, we have R, we have C. This is the current, which is the only current in the circuit, and here this is our capacitor voltage, VC. And this is the input driving the circuit, Vs. Suppose that Vs of t is some sinusoidal signal at frequency omega radians per second, okay, where A indicates its amplitude and phi is its phase. Find the current I of t and the capacitor voltage VCT in steady state. In steady state, okay. Since the input driving the circuit is sinusoidal, we're talking about the sinusoidal steady state. Okay. So the very first step is, which is written here, we're going to transform the circuit, which is the actual circuit, which is the time domain circuit, into the complex circuit, which we call the phasor domain circuit. Okay, and the notation is such that we capitalize the lowercase letters. Lowercase letters indicate the time domain signals in general, and their capitalized versions indicate their phasors. Okay, these are functions of time, whereas their phasors are constants. So in a sense, in phasor domain, what we're dealing with is we're solving a DC circuit. Okay, DC and LTI resistor. Okay. Now, here goes the solution. First, obtain the phasor domain circuit. Okay. So, we have the same picture, but now the variables are indicated by different letters, or the same letters but capitalized versions. Here we have capital V of C, the phasor of the capacitor voltage. Here we have capital I, the phasor of this current, I of t. Here we have capital Vs, the phasor of this lowercase Vs of t in time domain. Now, what's capital Vs? There's nothing to compute really, it's already given. So this is the time domain representation. So what we do is we take the amplitude, we take the phase, and obtain the complex number. Okay, with magnitude A and phase phi. Okay, this is just another way of writing A e to the j phi. Okay, and then what else? We replace all the components, passive components, by their, or represent all the passive components by their impedances. As for resistor, nothing changes. Okay, here we have the resistance R in phasor domain. Still we have resistance R, which is measured in ohms. Whereas for inductors and capacitors, we have the following transformation. Here we have capacitance in farads that we transform into the impedance of the capacitor in ohms. And the impedance of the capacitor is 1 over j omega c. Okay, so that was figured out in our previous lectures. Okay. The important thing about phasor domain, or the simplification that phasor domain circuit brings, is the following. Here we have farads, and also if we had an inductor, we would have had henries, but now we have no farads, no henries, everything is in ohms, okay? Because the ratio of voltage to current is constant. Okay, now since we have an ohm here and ohm here, two impedances, and this thing we can treat as a time domain circuit, we can simply combine these two impedances and obtain the equivalent or effective impedance, which would make the circuit easier to solve. Okay, so this therefore is equivalent to, at least from the current point of view, to the following circuit. Here we have the current, here we have a phi, and here we have the impedance. Okay, equivalent impedance of this resistor and this capacitor, and the equivalent impedance simply is the sum of this plus that, because these two components are connected in series. So Z equals R plus 1 over J omega C. Okay, and now what we're going to do is we can figure out the current easily simply by dividing the voltage by the impedance Z. Okay, and once we have this current I, that current times the impedance 1 over J omega C will give us the phasor V of C, the phasor of the capacitor voltage. And once we have capital I and capital VC, all that remains is to transform them into the time domain, which is quite easy because we know the frequency. Frequency is omega. Okay, so let's do that. Z equals R minus J 1 over omega C. So we carry this J upstairs. That's why we have a minus sign here. And let's write this complex number in polar form. So we have the following magnitude: R squared plus 1 over omega C square, and then we take the square root. And then how about the phases minus arctangent, this thing 1 over omega C over R. Okay, minus arctangent omega C over R. Okay, so this simplified a little bit gives us the following: omega R C squared plus 1 over omega C. So that's the magnitude, and we have the phase minus arctangent 1 over omega C R. Okay, so that's R Z. And then what's I? I is simply voltage divided by the impedance. Then the current, or the phasor of the current, is the voltage of the source divided by the impedance seen by the source, which is a omega C over omega RC squared plus 1 square root. And then we have the phase of the source minus arctangent 1 over omega CR, which makes plus arctangent 1 over omega RC. Okay, so when we're doing multiplication or division, it's easier to deal with. Polar representation. If you're doing subtraction or addition, it's clearly easier to do that in rectangular representation. Okay, so that's our current with magnitude and phase. Okay, it's from now on it's quite straightforward to obtain the time domain representation of it. We'll have a sinusoidal signal with amplitude this amount, and the phase 5 plus arctangent 1 over omega RC. And the frequency of oscillations is omega. That's the oscillation frequency for the input. So that's R1. How about the capacitor voltage? Okay, this is the capacitor voltage. We now know the current I. It's simply the impedance of the capacitor times the current passing through it, just like a resistor. So V of C equals 1 over J omega C times the current. Okay, and that's 1 over omega C. Let's write it in polar form. This J goes upstairs as minus J, and minus J is e to the minus J pi over 2. So this is a complex number in polar form with magnitude 1 over omega C and phase minus 90 degrees. Minus pi over 2 times the current I, which equals, here we have the current A over 1 plus omega RC square. Okay, and then we have phi arctangent 1 over omega RC plus minus pi over 2, minus 90 degrees. Okay, so that's our voltage phasor 2. So we're done in phasor domain. Now what remains is step 3, which is we carry everything to the time domain. Namely, we're going to write down I of t and Vc of t in time domain. And that's easy. One directly gives us the time domain I of t, which is a sinusoidal signal with amplitude written over there. I of t equals a omega c 1 plus omega rc square. Okay, so that's our amplitude, cosine. Frequency is the frequency of the input, omega t, and phase is what appears here. Plus phi plus arc tangent 1 over omega r c volts. And the second expression, which is the phasor for the capacitor voltage, will immediately give us the time domain signal Vct. The same thing here. We have the following amplitude, 1 plus omega rc square. Okay. Cosine omega t, the same frequency. In fact, all the signals in our circuit, all the currents and voltages will have the same frequency, omega. And then as for the phase, we have phi plus arc tangent 1 over omega rc minus 90 degrees. And we're done. Okay. Now let's move on to our next example. Here is our next example. Okay. 1 Henry's. Okay, and we have two other inductors, 0.2 Henry's, 0.4 Henry's, 5 microfarads, 1.25 microfarads, and the input is 4 cosine 1000 t plus 45 degrees volts. Okay, now in this circuit we're interested in figuring out this capacitor voltage V and the current passing through the this 0.1 Henry inductor, okay, or the current extracted from the source. Okay, so find the particular solutions. IPT and VPT. We're going to figure out the particular solutions for this current and for this voltage. Clearly, we can apply the phasor domain analysis technique because the input is a sinusoid with frequency 1000 radians per second. Okay, so let's go ahead and obtain, as our first step, the phasor domain circuit, which is, okay, note that this time domain circuit is of order, well, we have 5 dynamic components, but the order seems to be 4. In any case, it's not a simple circuit, but thanks to phasor domain analysis techniques that we have just developed, this just becomes a circuit of degree 0 in phasor domain because it's an LTI resistive circuit in its phasor representation. Okay, here is the solution. Equivalent circuit in phasor domain at the frequency omega, which is determined by the frequency of the input. At frequency omega equals 1000 radians per second. Okay. Now here we have henries and farads. In our phasor domain circuit, everything will become ohms. So okay. Now here we have, first of all, the phasor representation of our input, a complex number with magnitude 4 and phase 45 degrees. Unit is the same as unit in time domain, which is volts. Here we have J omega L for the impedance of our inductor. Omega is 1000, L is 0.1, so this makes J 100 units is ohms. So henries are transformed into ohms. Okay, that's the whole beauty in it. Likewise, we have here a capacitor 1 over J omega C. Okay, being the impedance, omega 1000 C 5 times 10 to the minus 6 farads. So that makes minus J 200 ohms. Okay. And the remaining impedances can easily be computed to equal J 200 ohms, and this is minus J 800 ohms. Okay, and these are the phasors that we are after. This current I, and also the voltage of the capacitor. Okay, this voltage V. Okay. Now let's simplify a little bit this circuit, which we can because there are a lot of connections that are either parallel or series. So the first step, a possible next step, seems to be as follows. Okay, from the circuit obtain the following equivalent circuit, at least from the current point of view. Here we have J 100 ohms. This is the current that we are after. This is our input voltage, 45 degrees volts, and here we have two impedances, Z1 and Z2. Now what's Z1? Z1 is, here we have an impedance and that's in series with another impedance, so we can simply add the individual impedances to obtain the effective or equivalent impedance. Okay, J400 plus minus J200, that yields J200 ohms. Okay, likewise here we have J200 and minus J800, and that makes minus J600 ohms. Okay. Then this is, let's call this I1, and let's call this current I2. Once we figure out I, we can simply compute I1 and I2 by current division. We can apply all those techniques that we're familiar with from LTI resistive circuit analysis. Okay, and once we have I2, this V, or this V, simply is I2 times the impedance, which is minus J 800 ohms. Okay, so let's move one step further and combine these two impedances into a single one. Okay, so that's further equivalent to the following. Plus minus, we have 45 degrees volts. This is J 100 ohms. This is the current that we are after. And here we have Z, the equivalent impedance for this parallel connection, okay, which equals inverse of the sum of admittances, and admittance simply is 1 over the impedance. It's the generalization of conductance. Okay, so the impedance for this guy is 1 over J 200, and impedance for this guy is 1 over minus J 600. Minus J 600, and this sum give us the equivalent admittance, and then we take the inverse of that to obtain the equivalent impedance. Okay, and now this equals J 200 times minus J 600 divided by the sum of the impedances, J 200 plus minus J 600, and this yields J 300 ohms. Okay, so these two guys give rise to an equivalent impedance of J 300 ohms. Okay, now it's very easy at this point to compute I. All we have to do is divide this voltage by the impedance seen by this source, which is J 100 plus J 300. Okay, so I equals the voltage divided by the equivalent impedance seen by the voltage source J 100 plus J 300. Okay, so that's 45 degrees divided by, since we're doing division, it's better to express everything in terms of polar coordinates. So this is J 400, so the magnitude is 400. It's multiplied by J, therefore its phase is 90 degrees, or pi over 2 radians, 90 degrees. Okay, and this yields 1 over 100 with phase 45 minus 90 degrees, okay, minus 45 degrees, or minus pi over 4 radians. What's the unit? Unit is amps, okay, just like in time domain. Okay, we have figured out I. From this, it's apparent what I of t, okay, the signal in time domain, will be. But before going to time domain, let's also take care of this voltage, and then we will be done in phasor domain. By current division, okay, which we're familiar with from circuits that are LTI resistive, but now since phasor domain circuit is just like an LTI resistive circuit, we can apply this method. Okay, by current division, I2, okay, this current equals, okay, Z1 divided by Z1 plus Z2. These are being Z1 and Z2 respectively. So we have J200 and J200 minus J600 times the current I, which is minus 1/2 I, and that's minus, this is I 200 minus 45 degrees, okay? Now this is not really incorrect, but to make it more correct, because this representation says that here we have the magnitude and here we have the phase, but magnitude cannot be negative, therefore we have to take care of this minus sign, which we can easily do by carrying it inside the phase. Note that multiplying something by -1 simply means adding a pi radians phase to it, or 180 degrees phase to it. So this, in other words, equals 1/200 with phase -45 plus 180 degrees. That makes 135 degrees. Okay, so, and that's amps. So that's I2, which is this current. And then V simply is I2 times the impedance, minus J800. Okay. So finally, V, the phasor of the capacitor voltage, equals the impedance of that particular capacitor, which is minus J800 times I2, which we just computed to equal this. Okay, so that's 800. This minus J produces minus 90 degrees of phase. Okay, so this is minus J800 in polar form times I2, which is 1/200 with phase 135 degrees. And this yields what? For the magnitude and the phases, plus 45 degrees. The unit is volts. Okay. So let me write it volts here. So that's our equation 2. And now we're done in with phasor domain circuit. We have the phasor of the capacitor voltage. We have the phasor of the source current I. All that remains is transform those complex numbers to their time domain representations. Okay, equation 1 immediately yields that the particle solution for the source current equals the sinusoidal signal, whose magnitude is 1/100 amps or 10 milliamps. The frequency of oscillations is the frequency of oscillations of the input, which was 1000 radians per second, and as for the phase, it's sitting here, minus 45 degrees. Or pi/4 radians, okay, milliamps. So that's our IPT. And as for the voltage, okay, for the capacitor particular solution is the same thing. Here is our phasor. So in time domain, it means a sinusoidal with signal with magnitude 4. The frequency of oscillations 1000 and the phases 45 degrees or pi/4 radians. Volts. Okay.